Hi, I'm John Michael Hand, Senior Director of Product Planning at FADU. This is a presentation I gave at Flash Memory Summit 2024 on how new energy-efficient SSD controllers can dramatically improve data center TCO. This was a very cool panel. I got to present with a fellow from Microsoft, and Meta was presenting on SSD telemetry and OCP NVMe SSD spec, as well as Samsung. This is a very cool panel. Unfortunately, it didn't get recorded, so I'm kind of going over my session. And the idea was I did write a lengthy blog post on this topic, and the idea of this presentation was to basically kind of describe all the sections in the blog post. So the first part being, kind of this data center SSDs versus consumer SSDs and trends in power efficiency, talking about how the impact of controllers to first NAND power on SSDs, power states, and I'm going to do some demos for some of the tools we built to kind of understand some of this data. And then one of the key case studies on how actual drive level power efficiency impacts rack level TCO. And then, kind of pulling it all together, quantifying the benefits and the impact of sustainability and energy efficiency. So one of the most common misconceptions I see is, between data center and consumer SSDs. Now, people in our industry are generally pretty smart and understand the differences, but outside of like the core SSD market, when a developer is using an SSD, especially like an AI developer or something, they're just using some storage. They're not necessarily understanding the complexities and nuances of data center SSDs versus consumer SSDs. But in the power efficiency standpoint, consumer SSDs obviously are mostly on the M.2 form factor. That form factor is literally designed to be kind of small and to basically fit in laptops and mobile devices. But those types of SSD controllers are really optimized. Well, obviously they're optimized for cost, but those workloads, the consumer type workload, is very bursty, where you're basically installing an application once or installing a game, and most of the things, most of the workload on the drive is reads, and most of it happens all at once when you're loading a game or installing an app. So the drive basically sits there idle 99% of the time. So when the drive is idle 99% of the time, the obvious thing to do is to just turn it off when it's idle. And this is something that they do. It's called PCIe L1.2 substate, which is like a zero idle power substate. These transitions happen autonomously through something called NVMe autonomous power state transitions, so that they have like a non-operational power state in NVMe Express. So the idea is that when you resume from a near zero idle power state, in an SSD that might take, consumer SSD that might take 4 or 5 milliseconds, but that's not a big deal for a consumer, right? That you barely would notice when you're waking up your laptop. But 4 to 5 milliseconds in a data center application would be catastrophic to the latency, because random read latency on SSDs is in the tens of microsecond range. So something like a 5 to 8 millisecond resume would be very bad. But again, the technology for zero idle power on SSDs has been there on consumer SSDs for a long time. Now, I do believe that this technology will eventually make its way to large capacity QLC drives, because it just makes sense. QLC drives that were, transitioning from a hard drive workload and say an object storage workload that may be doing, 50 to 100 megabytes a second average. Well, if you move that workload from a hard drive to an SSD, that SSD is going to be idle a very high percentage of the time. So I do believe that this like low power tech will eventually make its way into QLC drives, because it just makes sense. It's really a function of how much idle time does the drive drive spend in. Data center SSDs, on the other hand, this is like for the compute market. They're optimized for continuous workloads and steady state performance. The drive typically is meant to be used 24/7, and if the drive is idle ever, that would be kind of a misuse of the data center operator. Now the way that these drives are managed today are through NVMe power states, and we're going to go describe how that works in detail with some examples. But you can basically cap the drive max power, and for a compute type drive that's being used in compute workloads, the critical power efficiency metric is performance per watt in the active state. And so you're basically running a workload and then measuring the power it takes to run that workload, and then you're describing that workload in performance per watt. One of the things that we talk about in the blog post is controller versus NAND power, and the It's not. It's a little bit more complex than this. Obviously, there's other things on the board like regulators and DRAM and then those stuff. Maybe we'll just say maybe that's 10 to 15% of the power. But I'm kind of making this really simplified, to make it easy to understand. But the overwhelming majority, like greater than 80% of the power of an SSD, goes to the NAND and controller. And so if your controller, typically we see Gen 5 16-channel controllers from competitors at like say 8.5 to 9 watts. And the FADU controller basically consumes 5.7 watts in the active state. And so if you look at when power is capped, and again we'll talk about many reasons why this is done. The percentage of power that goes to the NAND is directly proportional to the performance per watt, because if you're able to give more power to the NAND, you're able to deliver more performance from the NAND. And so we basically, in the blog post, I have this little little diagram here. It's a little interactive chart where you can basically kind of move down to like say 10 watts. You can see at 10 watts, 5.7 watt controller, we're able to do 57% to the controller and 43% to the NAND. But if you had an 8.5 watt controller, that would be 85% of the power to the controller and 15% to the NAND. And you can kind of move the slider up, and you can see obviously if you go to this higher power, it's 22 watts, then that that delta on the controller power is not as impactful. But the hyperscalers run in this 14 watt to 16 watt range, especially so for a 3.84 terabyte drive in the OCP NVMe SSD spec, they run at 14 watts. And you can see this is a stark difference. You can't run a controller very efficiently that's 8.5 watts at a 14 watt TDP, which is very challenging. So if we go back to our kind of diagram, the key impact, the key understanding metric here is that the higher a controller's power consumption, the more performance loss, the reduction in performance when the total power budget is capped. And so if you're capping that power, the higher the power of the controller, the higher the impact of performance is going to be. I mentioned that hyperscalers are used to running the drives at a lower active power state versus what the max of the form factor can support. And in the blog post, I described that, basically the E1.S form factor was designed to go up to 25 watts so that it could be similar performance of a U.2. Again, that was one of the main value propositions. You could have U.2 performance in a smaller form factor. But some customers may not want to run that drive at a full 25 watts because they actually care about TCO. This is very important when you have a very dense storage design. These small changes in power start to add up. So you can do a NVMe identify controller command, and if you do the -H, that's for human readable, it'll tell you all these active power states. And here you can see this is basically our drive is an OCP NVMe SSD 2.0 compliant drive. So these are the power states that are described in that spec. Power state 0, 1, 2, 3. This drive, like a 7.68 terabyte drive, might take about 19 watts on the FADU drive maximum. And so if you look at like in that drive, that power state 0, 1, and 2 would be equivalent performance. But hyperscalers are running that drive, 7.68 terabyte drive, at power state 4 at 16 watts. And so if you wanted to basically figure out what power state the drive is in, you'd say NVMe get feature, and you'd say, basically save, and it'll tell you what power state the drive is in. And if you want to set a new power state, you basically just tell it, which power state you want it to go into, and then the S is for save. Extremely easy, one line to do this in NVMe CLI. So if we look at the other demo that I have on the blog post is basically just kind of measured results. So what we did was actually measure the power efficiency. So we measured the power, we measured the performance, and then we look at the basically performance per watt is performance divided by power, and you're again just performance per watt. Now in a sequential workload, your metric is megabytes per second per watt or throughput per watt. And in a random workload, your workload is measured in IOPS per watt. And again, IOPS and bandwidth are the same thing, basically described in different ways. But you can click on the capacity of the drive, 3.84, sequential read, sequential write. You can see something like sequential write. We're comparing versus PM1743, which was kind of the 16-channel first PCIe Gen 5 SSD that came out. Now, if you look at ours, this is 58% better performance per watt. If you look at a sequential write workload, sequential read workload, 37% better, random read workload 60% better. We're able to do 188,000 kilo IOPS per watt. So this is 3.1 million IOPS on this drive. So this is kind of a nice way to kind of look at the power efficiency versus versus another drive. But again, just we want people to start thinking about this metric in performance per watt. The hyperscalers have figured out a trick, which is if they can run the drive at a lower power, they can run the fans at a much lower speed and reduce the total cost of ownership of that deployment in that server. So one of the key metrics I mentioned in the hyperscalers are running these drives at 14 and 16 watts, even though they are leaving a little bit of performance on the table. Maybe they might be running them at 20% lower performance than the theoretical maximum. Now, why do they do this? A E1.S, you can basically cool the drive. The 15 millimeter, 25 millimeter has nice heat sinks on there, and you can run the fans at a much lower speed. And the drive temperatures can operate pretty high, kind of up towards their whatever the limit of the operating temperature range is, because NAND actually likes to be hot. It's actually the controller that you're really worried about as far as controlling operating temps. And most of the temperatures on the drive are kind of mandated from basically a technician being able to hot plug the drive. It's like literal case temperature so that somebody doesn't burn their hand. So if you're running, the comparison we're making right here is running a drive at 16 watts. We'll just say a theoretical competitor is running their drive at 25 watts. Again, that's the max. We picked a Supermicro server. This server supports, this is a dual Sapphire Rapids or Emerald Rapids Intel CPU platform, and it supports 24 E1.S, and these are full PCIe Gen 5 by 4 E1.S. So it supports 15 millimeter or 9.5 millimeter in this, I think 24 drives across this. And in the server power, I'm calculating CPU, DRAM, motherboard, NIC, and I'm just kind of assuming the maximum CPU power here of I think I'd picked a 32 core. And we have in the blog post, we have a link to the total TCO model, which I described this in. But if anybody has used these 1U servers before, they know that these 40 millimeter fans, which are notorious for being extremely loud, also happen to consume 30 watts. So in this server, there's actually 8 of these 40 millimeter fans and 24 SSDs. So if you reduce the power, from 25 watts to 16 watts, there's an obvious reduction in the SSD power. You can just do the math. 25 minus 16 times 24. But the thing that's not obvious is the fan speed reduction is very big impact to server power, because you don't have to run the fans at 100%. The fans will run at whatever the hottest component in the server is. So if the SSDs are running at 25 watts and there's 24 of them, the fans will run at 100%. And if you're running at a lower TDP, you can reduce the fan speed because you can kind of tune it to basically figure out what the right fan speed is to have if you can tolerate a higher operating temperature on the SSD, then you can reduce the fan's power by from 100% to about 30%. And in this example, I just said this one server, I could actually reduce the total server power by 26% just by reducing the E1.S power from 25 watts to 16 watts. So again, it's not just the SSD power, it's also the SSDs and the fan. Now, when we take that same concept and look at how does that make a difference at the rack level, we can basically decide a standard kind of rack, and we just said a 15 kilowatt rack, which if you do the math, 250 at PDU running at 3-phase, it's something like 16 kilowatts or something like that. But we'll just say this is close. We just said, what is the max number of servers you can fit at the power levels that we just described on the last slide? How many of those servers can you fit in 15 kilowatts? And if you're running that lower power, you can actually fit 45% more servers and still stay in that 15 kilowatt envelope. And that's really important, because if you're looking at TCO dollar per terabyte per month, obviously one of the big things you can do to reduce TCO in a storage deployment is to use bigger drives. That's why we kind of are showing the 7.68 and 15.36 here. But this graph, you can see the TCO model in the blog post. We have a link to the TCO model if you want to know kind of how we calculated that. But this light pink is the CapEx per terabyte per month, which is largely dictated by the cost of the drive, and the server. Again, if you have more servers, then you have to amortize more of the stuff in the rack to all the storage. And then this red is the OpEx per terabyte per month. So again, power, rack space, cooling, networking, and so it's obvious you're going to be reducing the TCO by by reducing the power from the servers. So and again, you get benefits of actually providing more scale and more servers per rack. We actually talked about this in the flexible data placement track, but flexible data placement is a tool that is able to reduce write amplification. So it improves performance, it improves endurance, improves quality of service. One of the things that is kind of understood or underutilized is that FDP will also improve performance per watt. It's kind of an indirect thing, but if you look at this drive, this was basically a simulation where we ran 8 different workloads at different write sizes to the drive. And you can see with FTP off, it was down here like 1500 megabytes a second. With FTP on, it was like 5 gigabytes a second. Now, the thing that's not obvious is both of these workloads are consuming the same amount of power. So if you're able to deliver 2.5 to 3 times performance at the same power, your performance per watt in that workload goes up. So FTP is not only a tool to improve application performance and endurance, but it actually also improves your power efficiency. And again, that's not directly, but indirectly. The final slide was really talking about quantifying the impacts of sustainability versus energy efficiency. One of the things we see pretty commonly, I spend a lot of time in the sustainability space, and through the Open Compute Project, we wrote a white paper that talks about this extensively, about all the different areas of sustainability. I think a lot of people in the ICT industry think that sustainability is only energy efficiency, and sustainability is much, much more. It's about transparency, reporting, and metrics, scope 1, scope 2, scope 3 if you're a data center operator or a device manufacturer, and about circularity and interoperability. But efficiency is very, very important, but it is one aspect of sustainability. Now, this year at the OCP Regional Summit in Lisbon, I was there, and Intel gave a presentation on one of the new metrics that OCP is developing called infrastructure utilization infrastructure utilization efficiency. And its IUE is going to be a new metric basically to classify energy consumption at the rack level. And it distinguishes between compute and non-compute power. And so you remember in that example I gave you with the fans, where the fans were consuming a lot of power. Well, those aren't delivering anything useful to the IT application. They're not delivering any useful amount of work. They're just fans there just to cool the components. And so we count that as kind of loss. And so what if you could basically add up all the power? And again, this isn't, people said, oh, doesn't PUE already account for this? Because it accounts for the data center cooling and all the overhead of the data center, to all the power that goes into cooling the racks and all that stuff. Well, it doesn't, because PUE only calculates stuff at the data center level. It's not calculating the servers, the fans in the servers are part of the server. So this metric is actually even breaking it down even more. And one of the examples Intel gave was like 40% of the power in a standard rack is actually wasted in thermal power, in idle power loss, in fans. And this IUE metric can basically help describe how to measure that. And again, if you wanted to properly disclose the impact of sustainability on energy efficiency on sustainability, you would do a life cycle assessment. But again, the key message here is as it pertains to this presentation, is that energy efficiency is really a key sustainability driver, and into this use phase, into like how much energy do you consume during this use phase. Obviously, the carbon intensity, basically is the energy coming from renewable sources or not, is also a very, very big impact to the carbon impact of that server. But just the efficiency of the rack, reducing that metric will make an impact on sustainability. But again, just to be clarified, sustainability and energy efficiency are very important. They're different concepts, and they kind of work together. So thank you. That was a lot of exciting things. Please go read the blog post if you haven't. We go into a lot of this stuff in extreme detail and a lot of the models. And again, the FADU controller is extremely power efficient, and there are huge benefits to that architecture, and we really are excited about this controller. And all right, so thank you. Bye-bye.